Hi everyone, welcome back to our channel. I hope you and your family members are doing good because that is the most important thing. And for rest, we are here to talk. So we were following our pattern-wise DSA sheet. Topic was binary tree and the pattern is lowest common ancestor. So today we will solve the very first question, which is very important from the interview perspective as well, which is lowest common ancestor of a binary tree. So let's read the problem statement. It says we will be given the binary tree and we have to find the lowest common ancestor, which is basically parent, of two given nodes. So we will be given the binary tree and the two nodes and we have to find their lowest common parent. So if you can see the example number 1 for 5 and 1. For 5 and 1 the common parent is 3. Now let's check for 6 and 2. So for 6 and 2 the parent is 5 also, common parent, and the common parent is 3 also, correct? So for 6 and 2 the common parent is 5 also and 3 also. But 3 is the grandparent, correct? And 5 is the parent. So basically, as per the levels, can I say the lowest common ancestor or parent is nothing but 5 for 6 and 2, and that's what we have to return. So this is the question. Now let's see the constraint. It says the minimum number of nodes will be 2, definitely, because as the question also says na, ki there will be 2 nodes, P and Q for sure. So minimum will be 2. Now 10 power 5. The maximum number of nodes can go till 10 power 5. So we have to think for the linear code, 10 power 5. We cannot think for n square code. Why? Because 10 power 5 becomes 10 power 10. And you know, if you watched our time and space complexity video, that beyond 10 power 8, it's not safe. It might give us TLE. And for sure at 10 power 9, 10, so it will give TLE. Correct? So that's it. And node value can also go till 10 power 9. Okay. So basically, you know, integer holds the value up to 10 power 9. Beyond this, we have to convert this into long format. But as we are not doing any summation, multiplication with the numbers, so hence it's on safe side. So we don't need to, like, you know, store the values in the long format. That's what we understood. Okay. Now here is the question we have. Okay. LCA we have to find. So now let's see, as per different P and Q, what will be the parent. Now the question says now minimum number of nodes will be 2. So suppose the tree looks like this, 1 and 2 or 1 and 2. For sure the node will be there, parent will be there, and then either of left or right child will be there if total number of nodes are 2. So in this case, what will be the answer? 1 and 2. What will be the answer? For 2 the parent is 1, and for 1 no one is a parent. You can say consider itself. So out of these, the common parent is 1. So we are expected to return 1 from here. Similarly, 1 from here. Okay. So we saw one thing, ki no need to return like this. It's not necessary that the tree will look like this only. Then only there should be common parent. A node can also be its common parent. Okay. Okay. That's it. Now let's see one thing. Suppose we have to check for the common parent for 5 and 8. Okay. So for 5 the common parent, like the parent is 3. For 8 the parent is 1. But this is not the common parent. The next parent is 3. So it's not like out of grandparent, grandparent or parent we have to return always parent. We have to return that parent which is common for both the child, which is P and Q, which will be given by the question. Okay. Okay, clear. So, like, what do you think? What approach we should think here? Like, how can we think, like, how to write the code for this? Because in the start, without seeing the solution, it will be tough. But let's break it down without directly hitting the solution. How to think for such approaches? Okay, so we are at 3. Suppose, think for the worst and all case scenario. Suppose P is 3. Let's say P is 3. And Q is anything, let's say 0. So if P is 3, Q is 0. Okay. What do you think? In this case, what will be the parent, common parent? Can I say 3? So for 3 and 0, the common parent is 3 only. Because for 0 also common is 3 and for 3 to 3 itself. Okay. So do you think when we actually found one node at initial stage, do you really think we should go down? Because anyhow, we have to return 3 only as an answer. So do you actually think we should go down? I don't think so. Okay. So can I say if my root value root can be any node I'm saying. If root value matches with either P or Q, return the same root as an answer. Can I say that? What I thought. So I'll write this. If my root is equal to P or my root is equal to Q, I want to return what? Same root. Can I say this? Okay. Now suppose P and Q is different. Suppose P is now 5, let's say 5, and Q is 1, smaller ones. Okay. So now at 3, so we can say ki no, it's neither matching with 6, like P, and nor matching with Q. Okay. So now our task is to go towards the left side and go towards the right side. Can I say that? Okay. And remember, because we are returning root, so it's very important to store that in the root. Okay, like in the node type. Okay, you know that. I hope you know that. So from 3, we have to go towards left side and we have to go towards the right side. And as there is something in the return statement, so definitely from left side and from right side we'll get something. Correct? Okay. So because we are returning root, so can I say like when I will be at 5, like from 3, like at 3 it doesn't match. So when we'll go at left side, we'll check ki here the 5 is the root. Is it matching with P or Q? Yes, it's matching with P. So what we will return? Root. So from 3's left side, 5 will get returned. Can I say that? Now similarly, when we'll go towards right side, we'll check, hey, you are the root now? Yes. Are you matching with 5? No. Are you matching up with Q? 1? Yes. So okay, if yes, then return root. So from 3's right side we'll get 1. So from root's left side, 3's left side we got something. From 3's right side we got something. So it means left side is saying ki, hey, I am the parent, 5. Right side is saying, hey, I am the parent, 1. So root will say, okay, no, like don't fight, I am the parent. So root will say, I am the common parent. Okay? Okay, that's what we understood. So basically, can I say if after this we will call the same function for left side and we'll call the same function for right side? That's what we understood, so I'm writing. As there is some return statement, so we have to store in some left and right variables, so I'm storing it. After this, what we saw ki for 3's left side we got something and right side we got something. So when we will get something from both the sides, then root will be the, like 3 will be the common parent, correct? So we'll write ki if left is also not null and right is also not null. Okay? Return what? Root. That's what we understood, right? Okay. Now suppose P and Q is like, in this case, so it will return then and there. Why? 3 it will check ki 3 is a, but wait, we have to check for the null case also na, at first. So when the root is null, what do you think? What should we actually return? Null? If root is null, return null. So can I say if root is null, return root? Because root is null only na. Okay. So here only we will write one more extra case ki if root is equal to null or. Okay, so if root null or root is equal to P or root is equal to Q, return root. So if root is equal to P, P will get returned. If root is equal to Q, Q will get returned. If root is null, null will get returned. Very simple. Okay. Now here at the starting we'll check, is root null? No. Is root matching with P? 5? No. Is root matching with Q? 1? No. So now we'll go towards left side and right side. So first we'll go towards left side. Here now this has become the root. Okay. So in the stack call, first for function 3, now we'll go towards left side, so for function 5. Now for function 5, 5 is the root. It will check 5 is null? No. 5 is matching with P? 5? Yes. So return 5, root. Okay. So this function will get removed from the stack call and for its left side, we'll get 5. Now we'll go towards right call. So we'll go towards right call. So in the stack, in the like recursive stack, yes, for 1, it will get stored. Function call for 1. Now we'll check ki is 1 which is root null? No. Is 1 is matching with 5? No. Is 1 is equal to matching with like 1? No. So this matches, my bad. Okay, so root is 1 and matches with Q, 1. Yes. So return root, return 1. So this function will also get removed from the function call and it will get 1 as a right. Okay. So now we'll come here. Is my left null? No. Is my right null? Means left and right both are not null. So if both are not null, it means I am the common parent. For sure, I am the common parent. So we will return root as it is. So for this case, now we'll return. So this function will also get removed from the recursive stack. Okay. Now, this was for P 5 and 1. Now let's think for 6 and 4. Let's see how it works. Okay, 6 and 4. So what do you think for 6 and 4? What will be the common parent? Can I say 5? Okay. So now in the stack call, we'll save the function for 3. Now from 3 we'll go for function 5 left side, correct? Now again we'll go at function 6. Why we'll go? Because at all steps we checked root is not null. Yes, it is not null. And root is P. No, it is not matching with P. Root is matching with Q. No. So 3 and 5 has not matched with 6 and 4. Okay. So now when we'll come here, again it will become root. So we'll check, yes, this time it matches with P. So what we will return? We'll return 6. So 6 will get returned to 5's left side. Can I say that? So 6 will get returned to 5's left side. Now we'll call for 5's right side, which is 2. So for function for 2 will get saved. Now 2 also not matching, so we'll go for 2's left side. 2's left side. So function for 7 will get saved. Now 7 also not matching, so we'll go for left side. But now root will become null. So we'll get returned. Null will get returned from left side and null will get returned from right side. Okay. So both are null? No. So okay. When both are null, what should be returned? What do you think? When both are null, what should be returned? Simple. Null. Null. Why we should return null? See, when we are not returning null, we are returning something, it means we found it. Okay, we have found it. We have found 6, so we are returning 6. So if we don't have anything from left and right side, and if we are not the root is also not matching up, so I can say till now I have not found anything. So I can return null to the parent. So if both my left and right are null, return null. Okay. So if left is equal to null and right is equal to null, return what? Null. Just so why we need to return null. Okay, because not returning some value, returning some node, means we have found it, and if we have not found it, we will return null. Okay, so we will return null. So null will get returned to 2's left side. So this function will get removed, and to 2's left side null will get returned. Okay. Now what? We'll go towards 2's right side. So function 4. Okay. Now 4 we see hey 4 matches with Q. So return 4. So 4 will get returned to 2's right side. Yes. So 4 will get returned to 2's right side. Now this is something different case. What? In this case, first we have checked for when both are not null. Then we have checked for when both are null. Now the condition is if left null and right not null. Okay. So let's see. For 5, left side we have got 6. Remember? So for 5, because 5 is the common parent, right? So 5 should get not null value from the right side. Correct? And what is that not null value? The exact node 4. So we have found 4 here. So 4 is where we have received 4 at 2's right side. But from 2's left side we have null. From 2's right side we have not null. And 5 is expecting not null value from the right side so that it can announce itself as the common parent, which is lowest common ancestor. So can I say कि if left is null and right is not null, return right? Similarly, suppose if it was about 7, it was not 4. So 7 will get returned from here and from here null. But 5 is waiting for 7. So can I say कि if any of these child, whatever it is, left or right, if it is not null, return that. Can I say that? So basically, if, very simple, if left not null, return left. Yes. If right not null, return right. Can I say that? And that's it. That's it. This is the code exactly. But we have to write this in a arranged manner. Okay. So talking about the time complexity, obviously we are going on each and every node, so the time complexity will be O of n. And space complexity will be, as we are recursively calling the same function, and you know that in the stack we are going to save one node from each level. So that is height of the binary tree. So the space will be log n if the tree is binary, and if the tree is skewed like a structure like this, then the number of nodes will be, like the space complexity will be O of n. So let's write the code in the editor. Okay, so here is our editor. Now we will write the first case, which is if root is equal to null, or if root is equal to p, or if root is equal to q. If our root matches with any of these, we will return root as it is, correct? Done. Now after this we have to call for left side and right side. So we should store in a tree node left is equal to, we have to call the same function, correct, but with root dot left and with same pq. Can I say that? Now I will copy the same code for right side call, and here I'll make this right and here also right. That's it. Now I'll get left and right, and now our task is ki if my left is not null and right is not null, means left is also saying I am the parent and right is also saying I am the parent. Means if it is not null, means it is like it received something, correct? So in that case we should say ki okay, root is the parent, so return root. Okay, or else what we saw ki if left is not null, return left. If right is not null, return right. That's what we saw, right? When both are null, return null, correct? Okay, so collectively we can write like this: return left not is equal to null, return left or else right. Let me know if you understood this. Because if left is not null, see, in this case, like if both were not null, this would have passed. But if the line number 15 is getting passed, means for sure left is not null but right is null. So if left is not null, return left. Now if this condition is not true, like left is null, so if left is null, there can be two cases: right cannot be null or right can be null. So if right is not null, we will get right as it is. But if right is null, we will get null, because that's what we were expecting, right? Ki when our left and right both are null, return null. Correct? So I hope you understood. So this is the code in Java. I hope you understood. That's it. Let's try to submit this. Basically the time complexity is linear, so this will be the faster code only. So this is the code in Java. Here is the code in C++ with a similar approach if you are from C++ background, and here is the code in Python if you are from Python background. So if you understood this was the most basic approach which interviewer will expect you to answer for this question. But there is one more approach which I definitely want to teach you all, and this is very basic and very common. So for the second approach, the idea was ki suppose the P is 6 and Q is 8. Suppose the P is 6 and Q is 8. So ki, don't you think, like if you see this path 6 5 3 6 5 3, and if you see the path from this side, okay, 8 1 3. So the common was okay. Now similarly, let's see for if P is 6 and Q is 4. So can I say 6 and 5 and 3? We have to basically go till the grandparent, okay, or grandparent, whatever is available. And for 4, we'll write 4, 2, 5 and 3. Okay, so what was the first common? Okay, this is the approach, like this is how we are actually thinking, right? So what are we doing? We are going from that P node till the previous one, and how it is possible, because from parent we can go till to child, but from child if we want to go to parent, how to do that? If you have saw our previous video, we did what we did ki let's build the parent, like let's write the parent function where for every child we will store their parent in our Hashmap. So we'll start 3 with the null parent, and when we'll call the DFS calls for left and right, so for 5 we will send parent as 3, and for 1 we'll send parent as 3. And now when we'll reach here, for 5 in Hashmap we'll store 3 as parent, for 1 in Hashmap we'll store 3 as parent. So similarly, like using the build function, we will make the whole Hashmap. Okay, so for every node we will have their parents. Okay, so let's build a Hashmap. Why hash map we are building? Again saying, because we just saw कि from parent till grandparent, if we will be able to store this somewhere, and like from P, so we'll start from P to the head. Now similarly we'll start from the Q 4 2 5 3 till the head. And now the very first node which matching from the left side, from the Q to head, we will return that as a parent. Okay, so here we don't need to actually think for the recursive approach. Basically recursive approach is only needed to make that parent, like sorry, hash map, parent map. Okay, so let's write a build function. Okay, build parent function. In this we will get the root, and we will get obviously hash map to store and the parent. Okay, now what we'll check, first we'll starting from the root only na. So if our root is null, we will simply return. Okay, or else our task is key in map we have to put. So in map we have to put what? For root we have to put parent. Okay, now after that we have to call for, like recursively we have to call the build parent function for left children. So we will call the left child, okay, and parent will be root only, correct? Similarly we will call the build parent function for root dot right child, and parent will be root. So now what will happen, initially we will start from here 3, the parent for this is null, correct? So in the map we will make for 3 the parent is null. Similarly we will go for the next side, like left and right. So first we will go for left side, and for left the parent is 3 and the node is 5. So for 5 we have to store 3. So for 5 we have to store 3, correct? Okay. Now we will go towards right side, but before that first we are here, right? So we will go towards left side. Okay. So we will go at 6. Similarly for 6 the parent is 5, so we will fill this. Now we will go towards right side of 5, which is 2. So for 2 the parent is 5. Similarly for 7 the parent is 2, 4 the parent is 2. Okay, now for 1 the parent is 3, now for 0 the parent is 1, and for 8 parent is 1. Okay, I have filled this. So using this recursive function, which will take O of n time complexity, we will fill this. Okay, so we have the hash map. Okay, we have the hash map with us. Now what is our task? Our task is कि from P we have to start. From P we have to start, yes, and until it becomes null. Why it will become null? Because from P we are actually traversing to their parents. So for 6, from 6 we will go to its parent 5. From 5 we will go to its parent 3, and from 3 we will go to its parent which is null. So definitely it will, like both from, like if we will start from P and Q, definitely at one time so they will become null because of 3's parent null. Okay, so can I say कि while my P is not is equal to null, okay, we have to store all of this. So let's say we have to store in hash set. Okay, in set we'll save. So in set data structure we'll store. So we'll store like hash set dot add, we will store P. Okay, so first P is 6, so we'll store 6. Okay, now we have to move it to its parent. So P will become parent of it, right? So where is parent? In map. So map dot get P. So we have stored in map, how we have stored. So for 5 I want parent, so 5 is the key. So with 5 we will get the parent which is 3. So now the P will become 3. Is 3 null? No. So in the set please add 3 also. Okay, let's add it. Now again P will become map dot get parent of, get P means parent of 3. So 3 is null. So again we'll check here, now P is null. So please come out. So this is what the set we have. Okay, okay. So this line of code has actually helped us to fill the all the ancestors from 6. Oh sorry, my bad. For 6 the parent was 5, right? So sorry, we forgot to add 5. So after 6 the parent was 5 and then 3. Okay. So this while loop has actually helped us to fill all the ancestors from P to the head one. Okay. Now we will start from the Q side, and at whatever, like the very first position where they will match, we'll stop. Okay, so we are ready with this. Can I say that? We are ready with this path. Okay, now our task is to check the next one. Okay, so now again we'll start the while loop. Okay, so in this case we have to check. Okay, So in this case, we'll start from Q. Okay, we'll put in the hash set. Now we'll go to this 2, put in the hash set, and now we'll go to 5 and we'll stop. So what was the stopping condition? So can I say if at any time Q is already present in set, it means this is a duplicate and this is the first time we are heading towards the same node. So stop. Correct? So we'll check ki until our hash set dot contains Q. We'll keep doing this. And now what we are doing, we are at 4, right? So 4 is present? No, it's not present. So we have to move our Q to its parent. So map dot get Q means parent of Q. So what is the parent of Q? Which is 4. Parent of 4 is 2. So now Q will become 2. Again we'll check, is it there? No, 2 is not there. Okay, 2 is not there. 2 is not there. Okay, now again parent of 2. Parent of 2 means 5. Is 5 is there? Yes, 5 is there. So wait, stop, come out. Now what is the Q value? What is the Q value? Can I say Q value is 5? That's what the common one. So basically Q was the expected answer, so return Q. That's it. Okay, so what we did, we made this parent hash map with the help of build parent function with the DFS approach. And now we tried, because we have the parent node, so from the child to parent also we can traverse. So for, like, you can do from Q, like first what we did, from P to parent we did, and for Q we checked if it matches. You can do vice versa also, okay, from Q to parent store it, okay, and how we checked here, na, check if P is present in this or not. Now if you are thinking ki the time complexity, no, in this way the structure for P was smaller, but in the other case it might be larger also. Okay, so let's see the code for this. So here is the lowest common ancestor code with hashmap approach. First we'll make the hashmap, which we will call parent, and now we'll call the build parent, which is recursive function. Here we have made, okay, and now after that we'll make a set, let's call it ancestor, and now we'll run the while loop for P. Basically from P till head node we'll fit everything in the set, and now for Q we'll run one by one and we'll check what is the first matching number, and now we'll return that Q. Okay, that's it, very easy code. So let's run this. Again the time complexity will be O of n to fill the map, okay, and further because we are running 2 while loops but only for levels, okay, so log in, correct, but as n is the larger one, so linear will be the code, but in this code the specs complexity will be more because of the hash map and hash set. So definitely the DFS approach, which we discussed earlier, will be the preferred one here. That's it. Here is the code in Java, and here is the code in C++ if you're from C++ background, and here is the code in Python if you're from Python background. So with this, if you understood and actually made your own notes also, then we are done with the very first question of this pattern. And that's it, guys. If you understood, please make sure to comment down in the section, and please hit the like button if you really like the way of teaching. And that's it. I'll attach the sheet link and my social media link in the description. Let's meet in another video with some more interesting questions, topics and patterns. So then keep learning, take care of yourself and your family.